Hello buddy, welcome to another stream. How we doing? How's it going? Yeah, PBR. Welcome Agent, how's it going? So last stream we worked on quite a lot actually. We improved PBR. 2 seconds. There we go. We improved the PBR, but we also added image-based lighting, which is what you're seeing in the spheres and the background as well. But end of last stream we had a bit of a problem where the Fresnel wasn't looking right. It wasn't looking like this in this debugging mode when I viewed the Fresnel. And I found out the issue probably about half an hour after I finished the stream last time. Hey Gloria Sir, welcome back. How you doing? Yeah. Got the new trim. The hairdresser gave me this sort of like yeah, I got like a V going down the back of my head and I was like but apparently apparently it is good and it looks good, so it's good. But yeah, when I saw it first I was like, it's cool. It's always like that with haircuts. Just you know, after about a week, I'm quite happy with the hair. You know, I'm cooking 32 Celsius in here. Yeah, it's quite warm today. Here it's about 23. I just took a walk. But yeah, definitely feeling warm right now. Just out in the sun. Yeah, okay, yeah, you're not cooking, but you're being cooked. Yeah. So end of last stream, you see how this is brighter here? We weren't getting this. And I'll talk about why that is. You see the Fresnel here showing up? Now, I gotta talk about what this debug mode actually is. So we were copying, well not copying, we were inspired. Where the crap is my, this one. We're inspired by this shader and the way it does the debugging. I was like, I gotta have some of this in my game so I can debug and see what's correct and incorrect, basically. And in last stream, when we looked at the Fresnel debug option, it wasn't debug viewing the Fresnel term in the specular calculation. So even though it's under here, then Fresnel, it's not actually debugging the Fresnel in the specular that's used to derive the specular contribution to the lighting, right? Oh, thank you, Jack. Thank you, Jack. Welcome, welcome. So we was actually doing that in ours and debugging it that way. What this one is actually doing is using the environment specular color. So if I draw it, it will make a ton of sense. So with the Fresnel, if you have like a flat ground, you have the light here, or whatever, and you have your camera here. The closer you shoot your ray there, where is it? And you have the sun, the reflected rays going there. U ray, light ray. Right. So your light ray coming from here. That's your light ray. And your half vector is probably that. I think, so the Fresnel that's going into here is view dot half. So it's this vector and that vector, and the more perpendicular they are, the more the Fresnel would be white. So basically, the closer you are to the ground, the whiter it will show when you select this Fresnel viewer. So where is that? Right. So if I put the view and the light direction in there, and we view the Fresnel, as you see, the light is over in that direction, as you can tell from the balls. So the more you get closer to the ground with them, what is it? My controls. Okay, the light is coming from probably up there somewhere. So you got the light direction, which is the yellow, half vector, which is the green. And so the more perpendicular they are, the brighter it becomes. And then the more sort of the more parallel they become, if you will, the darker it is. So this is correct. This view mode is correct. But I was wondering why my view mode is not the same as this shader here. And that's because it was using the Fresnel from the reflect ray, and not the one with the light. So the fix. So what's actually wrong is when I did my reflect color, it was not doing it. It was reusing this Fresnel here, which was using the view in the half direction, which is basically halfway between the light and the view. So what it actually needs to be for the reflect ray is the surface normal and the view direction, and that is what is used in this debug mode. So put the surface normal back in there. That's what's used in the debug mode of this thing, and that's why it's bright around the edges. Because if you just draw it up, you got your sphere, you got your camera, you got your surface normal, you got your ray. That's perpendicular. This is going to be white. Go here, your surface normal is there. This is not going to be white because they're not perpendicular, right? So that's the reason why. So this was wrong when we did the Fresnel before, but now I've corrected it to use the surface normal instead of the half direction. So this is why we're getting the this is why we're getting this nice thing around the edge now here. You can see it's brighter. So we go to here for now. There's the brightness, and that is making the sort of reflected color brighter. Yeah. It adds a bit more to it. So today we're going to be improving this more, because right now if we increase the roughness, it just changes the normal distribution function, which causes this thing to get wider and dimmer. Or dimmer? Okay. It gets dimmer when combined with the geometry function, geometry shadowing. Is that right? No? No, okay, I'm wrong. I guess combined with the Fresnel then? Yeah, this Fresnel wouldn't be, it's not the same Fresnel it gets multiplied with. But yeah. No, Fresnel doesn't take in roughness. Huh. Yeah, I'm a bit confused then. How does that get dimmer? Oh well. Well, see in the maths with the mouse to see what it does. But yeah, it gets dim as soon as it goes, which it should do, right? Because it gets rougher. So that specular highlight should just disappear. One of the balls is flickery. Yeah, there's probably a glitch where it just near the edge of the screen or something. That's cool. I'm not fussed about that. We're going to rewrite the whole thing anyway. Looks nice. Doing another uni crap on the horizon. Oh no. Hopefully you break away from that soon. Summer holidays and all. So yeah, there's a couple of bugs to fix. There's the roughness one. So I think we'll start with that. So the basic idea with the reflection. So we'll turn up the metalness. We'll see it more. You'll see we see the reflection in here, and the rougher it gets, it's not making the reflection rougher. So that's because when we fire a ray, it will bounce off, and it will reflect into the sky and sample the cube map. So what's happening here is that you technically need to have tons of different rays that fire off, but that gets really expensive, and yeah, we don't want that. So the way around that is you basically cache it. So I think the solution we're going to try is if you look at our cube map. Oh, it's upside down. Great. If you look at our cube map, basically we need to produce different MIP level versions. And I think what we can do is we can sample with the roughness as the MIP. And that should get us, so if we downsample it, that should produce the equivalent of a rougher reflection, I reckon. So let's give that a go. What is that error? It's debug drawing the light normal and the half normal, or the half vector. Yeah, a vector towards the light and a vector between the camera. So view vector, light vector, half vector. So this is green, yellow, red. Wait, yellow, red. Yeah. Program drawing. So I think we can just try and quickly downsample. So I need to pop into here, and I want to sort of my texture viewer for a moment. When it comes to that environment map, we need to also register and say, hey, by the way, for the texture viewer, can you flip the image? Because it's upside down, and that will make it so that it's not upside down. We only have to do this for the swap chain, image, and screenshots. But obviously the cube maps obviously need it as well. Maybe, you know what, maybe actually. No. We should have that built into the GPU layer, because it's all cube maps will be the same. Flip. Or Resource type GPU resource type cube. Oh, this one. Oh, my days. Yeah, it's horrendous. I did not mean to make that. Yeah. It's bound to happen with enough balls and cones. Okay, so view the okay, that's the right way up now. So, like every good programming problem, it gets solved with a shader. We're gonna make a shader to downsample. I've made one earlier. So let's put this somewhere. Downsample cube map. Oh. Excuse me. So here we're gonna have the, I guess, this destination of source MIP. Texture. Wait a minute. You need to have it as a 2D array. What? Yeah, I have to make texture views. I'm gonna have to make some texture views because otherwise the descriptor won't be set properly. Actually, we already do that for the... Yeah, I think it's fine. So read write texture 2D array. Yeah, this worked fine. And then we want to know the slice index. So if you load from... Yeah, load and store into that, it should be okay. All there, yeah, should be alright. So we've got to find that down sample. I suppose we've done another down sample. Maybe not. Right, let's take this one. Downsample cube map. So here we probably just want to do an 8 by 8, I guess. So just 2D 8 by 8. We'll probably dispatch across the destination, which would be the smaller MIP, and we'll sample a 2 by 2, and then yeah. So so this is a very specific downsample or downsampler code. which is, yeah, very custom. So we just got to figure out how different, what to delete and what to change. So use the source texture. Huh? That reads wrong. Okay, so the destination is going to be the destination would just be this, and the base source would be bigger. So the source base coordinate. I guess it'd be a multiply then. Right. So I think we want to sample from the source. The coordinate is going to be the source base coordinate dot +0. So you sample 2 by 2, and then the layer index goes in there. Alright, and then at the end we do a store. Oh, this is interesting. We used to use wave intrinsics. Right, okay. Again, that previous code was very specific for a different downsampler. So this one, we want to make sure. So we say if so our destination goes out of bounds, then we can. We need the dimensions passed in. Destination dims. And I guess you have a source dims as well, maybe? Yes, if any of those are out of balance, just return, don't bother doing anything. This is a power of 2 texture. So for our, I guess we'll be safe about it. So what do we need to do when you get 2 by 2? What are we planning on doing? Do we take the average of those? Or do we just multiply? Yeah, do we multiply them all together? Or do we accumulate it? I think it'd be a multiply. Hey Majestic Mac, how's it going? Welcome back. How you been? So we're looking at loading from a array to the array. To the array U32. So you'll get a color back. Kind of packed though, isn't it? So color 0. See, if you multiply them all together in there, you know, and you've gone out of bounds, for instance, you would put a black there. So when you multiply it, it multiplies with 0 and everything just gets thrown away. Or if there's a black pixel, everything just gets thrown away. So maybe you're best averaging by adding them all together and dividing by 4. Yeah, it's something to think about. So we can do a thing where yeah, I don't think we would ever go out of bounds. Let's just not bother dealing with that. Because it's perfectly Power 2 texture for now. So let's just roll with that. So destination, DST coordinate, and install some final color. So how does one get this final color? So we've got a choice of averaging, multiplying, but again with that black it's probably not going to be good, and also summing, so just adding them all together. If you added them all together, things could get quite. You would keep the brightness, and by the time you compress down to a 2x2 or a 1 pixel at the lowest MIP or the highest MIP, you would end up with a very bright pixel. So I guess what we probably want is to just take the average. That's what we'll do. So we need to turn them into a proper. Let's just call it A for a minute. So yeah, it's a bunch of like, you know what? This is what it is. Linear, right? GPU, sRGB to linear, unpack, then that one, put on there. Oh shoot. Right. So, and there we go. So this has to be a vector 4. So sum all these boys up, compute. So F color 0, F color 1, F color 2, F color 3. Right, I think I put one too many ads. Did I? No, didn't put enough of those. Sweet. So now we've summed them all up, then we just divide by 4 and produce the final color. So that'd be color equal GPU linear to sRGB, pack back into a 32-bit int for me, please. And what I want to do is do a divide by a scalar, and I want to divide sum by 4, and voila. That should be the downsample. So we're going to try this out now, and we should see in our texture viewer the cube map being downsampled, and hopefully we can use this to simulate roughness for the reflex ray, and only have to cast a single ray. So let's give this a go. What did I do wrong? Type mismatch. Int does not cast or whatever. What int? Oh, sorry, I packed it too early, isn't it? That's why. Right, this was saying. Right, this wants to be a 2D array of. Right, and then this has to be something like a. Dot x. DST chord dot y, followed by the layer index. Alright. Oh. Cool. So now we need to plug this in. Okay, so we only really want to do this. I guess we could just keep doing it. Well, first of all, we need to change our texture. This is the environment texture. We want to say it's got MIP levels now. So let's just say it has 4 MIP levels. So it's 2K texture. So if you downsample it 4 times, that gets like 512, doesn't it? Quick maths. That's 2. Right, so 128. Hey, Sleepy Mushroom, how you doing? I want to ask about C. Is it good with OpenGL? Yeah, like OpenGL is written with the C API. So you should be able to, yeah, use C no problem. That's what I used. You know, it's mainly just a choice of preference in what you feel comfortable in language-wise. Hmm? But GLM mostly focused on C++. Yeah, again, it's just like personal politics, basically, isn't it? Like, either you like C++ or you don't. If you find that GLM is useful for you, use C++. C, yeah, it'll just, you know, if you like rolling your own stuff, then C is a good choice. So yeah, we'll go down to about 128 res. Let's just try that for now. We can always tweak it. Um, format 32 UN, because we're going to be accessing it as a storage texture, because we're going to read and write to it and not sample, because those are separate things. We've just written this shader and it contains a read-only texture and a read-write texture. These are storage textures. But we also have that sample texture, which is allowed to have a cube. Sample texture cube. Right, that's what we ended up putting in last stream. So let's fire this guy off. We probably want to keep notes somewhere of the number of MIPS. We probably want it shared between, so we should probably just stick it in the shared header file. This is shared between CPU and GPU code. This is the way. Environment map MIPS count. So we'll be using this when we want to interpolate between when we want to throw in our roughness to the sample function. Yeah, it's gonna be good. So when we kick off the frame start, I'll have to read back. None of this crap everywhere. Alright, let's do this again. Yeah, we are going to completely clean up this code soon. After we're done PBR and get onto the VVH thing, we're going to just restart this whole file. But for now, it's going to be messy. That's what progress looks like, messy code. So DST, we need to create a bunch of texture views. Let's do that quick. Shoot. Right, where's that environment map? Is there a base index somewhere? Yeah, MIP space ID. We'll make this. We'll not forget it. We'll do a nice for loop over every MIP. 0 environment map number of MIPs. What I think we would like to do is where's that base MIP thing? Right. Okay, so you do the get resource index and you add. Right, gotcha. You do that to the base environment map plus MIP. Oh shoot. Right, that goes in there. Source. So we've got to go over all the MIPs. Take one. Destination is always smaller than the Egotist. Thank you so much for the subs. I appreciate it. Welcome back. How you doing? Thank you. Less than 3 you too. Yeah, I think it's doing good, thank you. Had a busy weekend, catching up with sleep. And yeah, got my hair cut. And yeah, just been chilling, you know, went for a walk. Yeah. MIP maps. So they're the low resolution. You can have a chain of you can have lower resolution versions of textures in a chain, one after the other. That's what MIP is, MIP level. Hey there, CRC accounts. There we go. PBR, physically based rendering. So yeah, it's based rendering. I guess we'll put environment map dim in there as well. Well, so destination dims. So the destination dims is equal to E32 times 2 environment map dim. And then we're just going to divide equal that thing. I guess it's square. Oh well. BC destination dims 2. Alright, nearly there. So the source is bigger than the destination. Yeah, so you want to... Wait. Yeah, that's the right way around. So... nearly there, just gotta synchronize that we're reading and writing to this texture. And then we're gonna launch the cube map, downsample cube map across div roundup of destination dims and 8 for the X and Y's. Right, that's kind of looking good. We just got to initialize these base or these texture views now, because otherwise we can't target individual MIPs in shaders properly. So I just need to go and do that now. Something like this. So for all the MIP levels that we're going to have in this environment map, so this would be map texture view or map view 1 MIP level. It's going to have 6 array layers. Yeah, all 6 array layers we're going to view. I guess that's automatic actually. I don't know. Let's see. So base MIP, then that'd be environment map. So it's the first MIP level, set the base 1, and then this just asserts to make sure that it's linear. The IDs have been allocated linearly. Cool. So that should be what we're looking for. What I would like to do is actually comment out the code which is doing the downsampling, just to double check and make sure that everything is initialized first. So we're actually going to say that's already initialized and don't run it. Now, what was the architecture? Right. Nobody likes that woke rendering. Base is where it's at. Yeah. So they're not allocated next to each other. What a crime. Why are they not allocated next to each other? Tell me more, computer. Did I delete something? Did I... so those do their thing. Ah, the wrong assertion. Or the wrong condition. Right, so we put it back up. It still looks how it looked. We're going to open up the texture viewer. We're going to view the cube map. So now we should have MIP levels, right? Here we go, we've got 4 of them. They're uninitialized data as you expect, but they go down in, yeah, they go down in resolution basically. It's hard to see because the zoom adjusts when we change MIP. That's a feature of the texture viewer, but the resolution is changing. Oh, I guess that one didn't. What? I don't know. Yeah, I think when you do a zoom out far enough, it will obviously look like it changes. Something like that, I don't know. But anyway, so now we've got a downsample shader, which is going to average these pixels in a 2x2. It averages it. So let's take a look at that. Hopefully it doesn't blow up the stream. That sometimes happens if we index out of bounds. But I think we've written good enough code. We can just double check it one more time, just in case. So we get the dispatch index, if we're out of bounds, bail. Source index is this divided by 2, multiplied by 2, because destination is smaller, the smaller MIP. Then you'll get a 2x2 from that. Should be legit. From the source texture, getting new colors, unpacking, adding them all together, taking the average, packing it back in, chucking it back out. We didn't set layer index, so that would have just overwritten the same thing. So layer index. So actually, we have to do this for every layer as well. So it's a cube map. BC.layer index equal layer index. I think that's right. Yeah, you can do every side of the cube map. Alright, I think that's good. What's the arrow? If we hover over a sphere, it tells us the direction to the light. Right, if the stream does, I'll be right back, but it shouldn't die. Alright, we're still here. So let's take a look at the downsample. Right, so MIP1 got written to. Can we zoom in? So if we see here, what does it look like? Okay, that got downsample. Quite nice. MIP2, garbage. MIP3, more garbage. Should we look at the different layers? Right, 1. Bit weird. And MIP1. MIP0, still fine. Layer 2, MIP1. Complete garbage. So we're definitely... It's something from the other texture. By the looks of it, it's a bit weird. So going for every MIP, then for every layer. It would probably be better to do every layer than every MIP. Performance-wise, I imagine. Because it keeps saying... I don't know. Yeah, that wouldn't change anything there. Oh, we're doing the divide, aren't we? It's this and it. So this destination dims needs to be reset every time. And then we just keep dividing it until we've reached the lowest MIP. Right. And that should be what we're looking for. And then we can plug it into the shader and hopefully we see roughness. Yeah, okay, there we go. Sweet. So this is the downsampled version. It's the average. Now that's not looking rough enough. Maybe we need more MIP levels, but that's fine because it's a constant. We can just up a number and it all plays well. So let's put it to 8. I think that's enough. You can do that. Yeah, because 2 to the power of 11 is 2048, isn't it? So that's more than enough. Here we go. So we environment map. We got all these lovelies now. There's the downs. Right, so here's the rougher version. So hopefully, let's go to the lovely drawing board and hopefully I draw decent shapes this time. You got your camera. You got your sphere. This sphere is very rough. So when you cast a ray and you hit it, there's tons of like micro facet detail. You know, the micro facet is like bumpy or whatever, right? So when you actually cast your ray, you can get tons of different. I guess that's like ridiculously rough. There's something like that. You can get some. What's the way of saying it? The ray that's going here is basically simulating tons of light coming from different directions, and they all happen to go back that way. Right, it's a rough. Yes, it's a approximation of what's going on. Right, we're not simulating all of the light that's bouncing off this very rough surface. We're just doing a rough guess, or rough approximation. So the way we're going to do it is we're still just going to bounce it off like a regular reflector ray does and sample onto the cube map. But we're going to use based on how rough the surface is, we'll use the lower MIPS. And because we're using a linear sampler, it should blur it basically, right? It'll be an average between the 2x2 set of pixels it looks at. So hopefully, and obviously that 2x2 is not just 2x2 set of pixels at the highest res. At the highest resolution, it'd be tons of pixels, right? Because if you look at these 2 pixels here, when we go down to the low res, it's all of those pixels there. So the highest res, it's all the pixels here. So we're going to get an average of like, yeah, all that space and it'll be blurry. So I hope we got enough. Let's plug it in. So when we do that sample cube, calculate BRDF right here. That's the MIP level, right? With a linear sampler. I think it's set up right. Yeah, I think we put it. Yeah, let's just double check that. So in the Vulkan backend, when we create the sampler, where's the LOD thing? Min-max LOD, there's no clamp, right? Mip-map mode. So that is either, yes, that will become linear. Yeah, so it does the linear sample on the mip-map. That's good. So it will blend between 2 different mip-map levels as well. So you don't have to be, so you can put it in as a floating point number and it blends between the 2. So say if we put in 3.5, it'll be half of 3 and half of 4. It'll blend between those, basically. So what we can do is we can take the roughness. Now I think you might want to do something a little bit. Let's take a look at the this example here. I think they do what we're about to do. No, they've already pre-done it. You see this channel here, channel 1? This is already a very downsampled version of the scene. And what they're doing is they're sampling from 2 textures. And then they blend between those two based on the roughness times 4. That's interesting. I guess we could have done it that way, just had a really downsampled version. But you still would have probably had to have done the way we've done it. We have to have a MIP chain and downsample it until you get something like this. I don't know. Let's see how well ours works. So if we take the roughness, material.roughness, this is a value between 0 and 1. So what we want to produce is a value between 0 and number of MIP levels take 1. So it's as simple as scaling it by that number basically. Where is it? So there's 8 MIPs, right? So we scale it by that, take 1, and that'll get us a value between 0 and 7 as a floating point. So that should, fingers crossed, make it so that the rougher the surface gets, the more that cube map is going to get blurred in the reflection. Right, so we've got no roughness right now, or just above 0 roughness. So let's get to prime position. Now let's increase the roughness. Nothing happened. Great. So why is that what we think? Definitely got the level in there. We could put some rubbish in. Yeah, well, here's what we can do. If we disable the downsample, what we can see is we should be able to see the uninitialized data in there. So we turned up the roughness and we don't see that uninitialized data in there. To prove the uninitialized data is in there, open up the environment map, go to MIP. Oh shoot, it. Damn it. Did it not compile? Right, let's try it again. Is it just giving it back the same memory, and because it's uninitialized, it's crying out loud? You should have read the title. Yeah, hey, welcome back, Virgilia. How you doing? Yeah, I didn't PBR. So we're trying to get like nice looking spheres. We're getting there. We get in there. We're just trying to fix some issues, like here the roughness is only changing the normal distribution function. It is not changing the reflect ray. So we've just downsampled the environment map. And I'm trying to get it to... It's very weird. We should write black. Out. Let's just write our transparent pixel. Maybe. Okay, let's just write out blue. A really ugly blue. The only reason why I have a tiny grasp on how PBR works is because a seller Olus new video. Oh, who's a seller Lois? Do you want to drop a link? Doing good, working on your library. Awesome. Implement bindless textures. Sweet. What about bindless buffers? You got bindless buffers as well? Okay, so we don't see blue when we increase the roughness. Definitely blue in there. Whereas there's blue in the higher MIPS. So we're not actually changing the MIPS. Should we hard code? Right, so we've got blue in there now. Where's the cube sample? I thought... So if I put in there 4, we should see blue. Not seeing blue. So it must be something with a sampler then. Even though I thought we just checked it and I was like, oh, this is good. But I think we've... Linear sample mode. So map linear, okay. Clamp none. Clamp none. Put it to 1,000. What is going on? They have GLSR. Thank you, Jill. Appreciate it. This guy, yeah. Nice one. Thank you. I'll watch this one later. That was only done 5 days ago. Sweet. Thank you. I'll remember that and watch it. Thank you. Wait. Sample cube. You can do an explicit LOD, right? Sample LOD, is that what they call it? Sample level. Oh, texture LOD, that's it. Where's the cube? Yeah, they put the LOD in there, that's what I'm trying to do. So, it must... So if we hard code it, it doesn't show up. There must be some form of clamping happening somewhere. But where? So I guess this is where we use the power of RenderDoc. I just followed this dude's article on bindless textures. Fair play. I don't know, like, as soon as you've got bindless textures, right, you have bindless buffers. Yeah, just go full fully bindless, so then I won't worry about doing... Oh, is this guy write the... Oh no, okay, he's just got similar blog. Yeah, just you could make it do bindless buffers. Just go all in on the bindless. Very good. This is the way. If the i3D... Oh, the i3D stuff? No? What's that? My work is not as interesting. I'm building something to rewrite our 350,000 lines of testing code using using an ASD parser. My team wouldn't sponsor it, so I'm doing it on weekends. I make the new test at least half the F and half the size. Yeah. That's a bit strange to have to do in your spare time though. If it takes you a long time, I wouldn't bother doing it because, you know, you should get paid for doing work, right? If it's a long time, I could see it, you know, doing work in short time, but a long time. Bit crazy, right? Right, so change that. Take a capture. So if we take a look at our shader, where we do the dispatch, just got to figure out which one it is now. That's the UI. Sphere ray tracer, boom. Pop into here. Compute shader. Right, what is this? This looks interesting. So you got sampler in here. LODS, LOD 0 to 0, point sampler. Do we have any other samplers in here? Right, so it's looking. Our sampler looks like it's a point sampler, you know, not linear. That's weird. And then we look at our environment map. It only. But yeah, this one looks very strange. We can look at all the samplers. Maybe nearest. I might be returning the wrong one then. Oh, is there only one sampler? That it's picked up on. Okay, maybe I'm returning the wrong one. Clamp linear sampler. Clamp linear sampler. Linear. Oh, it's labeled nearest. Also, where's the names in this? Right, I need to do that debug naming thing. This should really be a function, but you know. Sampler, then with a name in it. Debug name. Sampler, object handle. VK sampler. Cool. So that'll set the name up. So we go into the render doc again. We should be able to see a proper name. Change the roughness just in case. Should be fine though. Take another capture. Now we look in the resources. What samplers have we got? Oh. Are we not uploading the samplers? Have we not been uploading the samplers this whole time? That can't be right. I don't think we've set our descriptors and it's just picking out a default. We create a null sampler. There's a null sampler and we fill all of the descriptor update tables with this null sampler. I don't think we've been setting these. No. Right, I've not been setting these manually when you create the sampler, so we've been using a nearest sampler the whole time. So we're not been using linear samples for anything, even in the UI. So my text rendering could look even better, or maybe worse. It should look better, and like everything should just look nice. Weird. Yeah, I don't know if we actually have too many places where we. Right. Okay. Interesting discovery, at least. Right, so the index would be resource index of res ID dot sampler equal resource backend sampler. There we go. So that should put it in the descriptor set. Now, so we should see something. Right, we see blue. This is good. So it's actually grabbing it at a certain MIP now. So if we re-enable the... So in the shader code, we need to remove this hard code of 4. Put in this roughness times the max number of MIPS. Because roughness is between 0 and 1. And this is going to be 7. So it'll be from 0 to 7. And now what we have to do is... Wait, what do I have to do now? Oh yeah, re-enable the... Yeah, don't put blue in there. In the downsample cube map. So it should see rough now. And... Dun 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 dun. Dun 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 dun. Here we go. It's getting blurrier. It's not quite what we wanted though. It's close though. When it's that rough, we should not see that much. We should just go all the way. We should probably have 11 MIPS. Then maybe we need to square the number as well. So it's a better. Right, so the number of MIPS, we should probably put 11, or maybe it's 10. Yeah, that'll give us a 2x2, I think. Look at that. So we look at the textures, environment map, look at the 11th MIP, or the 10th MIP. Alright, okay, that's a 4x4 then. You know, maybe that's okay because you got the sky here and you got the ground. Whereas if you did a 2x2, I guess you'd get that. Maybe this is fine. Right, so we look at that now. And we increase the roughness. So yeah, basically all goes. So it takes 50% roughness, you basically see nothing. And then towards the end, you really see a lot. So what we probably need to do is square the number, maybe? Or square root it. I just got to think about that. But that's definitely a good sign that we're able to get something working with that little hack. It's good. Hey Doro, how's it going? Welcome back. Hope you're having a good weekend. You don't have a management team. Wait. Painful to write high return for 20 or so hours of effort. You don't have a management team more interested in new features than better code base. It's pretty common. The disconnect from details of what sells the next big thing. Yeah, I guess I could see that there is a lot of focus always in new features. I do see that. But I guess, yeah. But still, like, I get, like, yeah, it should just be, Yeah, it's a game of trying to convince them because, yeah, doing it outside of work is really not ideal. But I guess it makes your working life better, and I guess that's the trade-off you're willing to make, which is fair. Which diffuse and specular B RDFs did you go with? I just went with the ones that are inside the video here. Not this one. This is a good video though. I'll link this one. This one goes over the physics of light and then how we cheat basically in 3D graphics and what we do, what we don't do. It's a really good video. I watched this like 8 times and I'm still learning stuff. But we just used the ones from this video from Victor Gordon. Where the ones we took his pseudocode and wrote it up and found that the shadowing function didn't work. So that's something we need to investigate. I grabbed it from somewhere else. But basically we used the for now, but we're gonna look at this in a bit. Fresnel. Yeah, so we used the Schlick. What a name. The Fresnel Schlick Smith geometry and Schlick Beckman. And then, oh sorry, it wasn't the geometry function, it was the normal distribution function. This was the GGX Trowbridge that didn't work, and then we found another one and it did work. So we're going to investigate into why that is today as well. And really, yeah, the right ones. Or the ones that we want. But yeah, so when you go towards the tail, so about halfway you start seeing it. More towards the end you really see it. So if I was to square 0.5 and 0.5, you get 0.25, right? You don't want that. So maybe what you want to do is a square root. If you square root 0.5 and 0.5, you get 0.707. So that will put you up here. So I think we want to square root this, so the way, so it's a non-linear damn it, where is it? Yeah, so I think what we would actually like to do is square root the roughness, and that will make it feel linear, but it's not. So let's try that again. Let's put the metalness up. Right. So it's starting to feel a bit rougher there. And then you really get up to the right, so it's pretty rough. You know what, I might add another MIP level. That also helps it. There's definitely feeling more. I don't know. Let's add another MIP level because that could. Because that's a 4x4. 2x2, 1x1. We got 2 more MIP levels. Alright, so we see the scale should be a lot different now as well. Just increase the metalness so we see it clearer. Oh no, emissive. Right, and then when it's fully rough, it just goes grey. Halfway, that's half rough. Maybe we need a couple of square roots. Yeah, Lambertian diffuse, yes. I didn't. Yeah, what other ones are there? Is that what you're using, Majestic Mech? Exactly. If this management team is worth, oh, this is worth. If it is less, sorry, Convincing the management team this is worth the effort is less than effort of a few weekends doing the actual work. Fair play. Yeah, I guess if it's only a few weekends, that's alright. It's not. It's tapering towards bad, but I guess it's not that bad. Yeah. That's cool. Well, that's really great. You believe in you're working that for something that much that you know, are willing to do that. It's only a few weeks. That's not bad. I thought it was going to take you like a lot longer because it sounded like a lot with what you said. It sounded like could have taken you months or whatever. Right, that's interesting. Disney uses something different. Um, so if we put the MIP down, I'm thinking about doing a couple of square roots. So let's take a look at max roughness and see how that looks. Metalness all the way up. Right, I think that's basically what you want. This is a 2x2 rather than just a 1 pixel at the highest MIP. You can see there's a bit of under and over now. And I think that's better because if we had it, it just would have been one color otherwise. Now you're seeing it an under and over. So I think having a 2x2 at least on the, yeah, really makes it more correct. So I think we want to do another square root because I think it needs to get rougher earlier. But I don't know. Maybe I'm just but we'll see. It's all about getting a feeling for what's right and wrong. So now it's getting rougher earlier. Right, I'm only just like a quarter in. And you already start to see the roughness. Getting halfway in, it's really like starting to show it being rough. 3/4, yep. Then all the way. Maybe what's the difference between 2.5? Yeah, I do like it, this scale. Yeah, I do like this scale. It's fine. Maybe a 2x2. You really see it. The anti-aliasing is real bad. Yeah, you already see it sort of. Maybe we should have a 4x4 instead. Because you start to see it being blurred pixels, I guess. Maybe. I don't know. Let's just try one more time. Where it says the maximum now. I guess you still kind of see it. So yeah, halfway is about there. That's half rough. Fully rough. Fully rough. Sure. It's alright, we can live with that. I think that's alright. Cool. So I think we can tick that one off. So let's add in roughness to the environment map. What is next on the agenda? We want to look at the geometry function, I think. Oh, sorry, the normal distribution function. Why does this one work? And why didn't the other one work? Lambda is pretty much the industry standard, but I've seen a few Oren-Naya special cases. Yeah, isn't Oren-Naya the way that this guy put it, and he said he would do another video, but he didn't. And I get that. Doing videos is so much effort on YouTube. But he was saying in this one that Lambertian is what you use for real time, basically. But the Oren-Naya is apparently more physically... Oren-Naya is more physically correct, apparently, but it's more computationally heavy. That's what this guy said. All right. I'm happy with that. I'm happy. What's going on? So, what is the next? So again, reflectance now, image-based lighting. We're only doing a single light still. We should probably do more than one light. But what I would like, so control materials and lighting we've done that in the UI. UI to control viewing each part manually, we've done that already. So now what these two left, I think we're quite close. I want to see my metals though. My metals seem a bit weird. We should probably try the other cube map as well, because we've got a nighttime cube map. And we should test them out in there too. But this GGX Trowbridge Rights, I think is how you pronounce it, should allow for roughness 0. Currently for roughness 0, things fall apart. Maybe we just max this with so we say, hey, this never goes below or reaches 0. So now if I put it at 0, it doesn't disappear. This used to disappear, this specular highlight. So I guess that's a fix. Can we reduce this down even more zeros? That goes well small, look at that. Bing. Right, it makes it actually disappear very small. If it's not that rough, that little highlight. So if we look at the normal distribution. That's another thing as well, is this... Oh, let's remove that clamp. Maybe what's happening is the normal distribution isn't shown through enough. And that's the reason why it disappears. Oh no, it really disappears. Okay, so I guess we can just put the up there at least. Is there a list for Renodoc supported extensions? I don't know. Like, it definitely doesn't support ray tracing, the ray tracing API. And it doesn't support... I think in general, he doesn't like to support extensions that are just... Like, it has to be the popular ones, basically. So there is the debugging... The extensions that support putting debug names on your objects. And obviously Renodoc supports that, because it means Renodoc can be like, hey, this thing's got this name. It doesn't support dynamic extended dynamic state either. Yeah, but that's not the one you was using because we spoke about this and you went to use the what was it called? Uh, Vulkan shader object. Yeah, yeah. So what you would probably want to do on that is you need in your game to say, hey, boot up for Renadoc in a Renadoc mode. And you might have to translate to using the layer. Remember those layers? Um, they have those compatibility layers. This one, Vulkan extension layer. Yeah. So what you probably have to do is if you want to use Renadoc, because there are times where it's just dead handy to use Renadoc, you probably just switch out to use this layer, and this will use the old pipeline system, and it basically does a pipeline caching thing, what people would typically do with a hash table. As when you change your state, it would, and you do another draw, it would be like, oh, yeah. Compile this pipeline and bind it, and if it's already compiled, it will grab it from the cache. So you're probably best just to do that. Right, I'm gonna take a quick minute break, but we got this fixed, I guess. That clamp was probably just good enough. But we want to look into this ggx tro bridge rights function and see like why this one didn't work. What is this one that we've put in because it come from somewhere else? And just investigate and understand this. So this is the normal distribution function. And then we probably want to double check the geometry shadowing function, make sure that's fine. Then double check geometry function, check metals, make sure those look good, and then check against the night cube map and just see how that one looks and feels. Yeah, then after this we could probably look at doing more lights because we just have one directional light at the moment. So it'd be good to just sort of do multiple lights and then probably improve the cleanliness of this code because we want to keep it, and it'd be good to document it for future me when I want to read back and understand this code that we've just thrown in here. Right, so I'll be right back. Alright, welcome back everybody. So, what is next on the agenda? Got a little list here now. GGX Trowbridge. Right, so this is the normal distribution function. This is the thing that makes that speck, a little dot appear on the surface of the thing you're rendering. It's that how much of the it's where the perfect mirror is that points to where the sun is, right? And oh, interesting. Yeah. So what are they using here? Did I get it from this one in the end? So the geometry. Sorry, why do I keep saying geometry? The distribution. So I think I took it from here, and this is the one that ended up working. No surprise. So there it is there. If we increase the roughness, you see it do its thing. Should we see if ours behaves like this? Quickly. Wow. I should have done that from my laptop. Okay, so what are we looking at? Geometry, sorry, normal distribution. So we increase the roughness and it gets bigger, bigger, bigger. And so when you see this one, mine just goes really white. Is that because the intensity? Well, intensity really plays a factor here, but also, why is the background appear white here? What are they doing in their sort of... Oh, we're whipping the n.l in ours, aren't we? They use like the... Yes, they just put it right in there. This is before the n.l is applied. Like if it was to... Yeah, you put the n.l on it, you see that it does have an effect. Obviously. But yes, R1. Bring the intensity down a bit. It gets a bit bigger, then it fades. Gets a bit bigger, then it fades. So that's basically what theirs does. See, I think we copied it. That's the normal dot, the light direction. That's the reason why I was making it only show up in the direction of the lights. So if we take a look, so they've just called it the normal distribution. Yeah, I think we copied this one in the end. Oh wait, -1 + 1. Ah, no. Right, no. That is the one from the internet. Sorry, from that shaded toy. But I had to rewrite the one above. That's strange. So this is one from the shader tool. I think it's similar. Um, right, it's definitely dimmer, more of a dimmer spec. Also, it's a bit strange how it doesn't really show up. I wonder what that... It's obviously how it gets used later on. But yeah, so this one here that we had that was testing a second ago, was that a copy of the... Oh, it was without the pi though, wasn't it? No, the pi's there. Yeah, so I think I just rewrote the one above. So obviously I've maxed that. N.H. Then there's this square of that. That's what that was doing. Then you multiply that by R2, so roughness squared take 1 plus 1. Then that as a whole gets squared. Right, so the powder's there. Then multiplied by... There's no max here though. So yeah, I guess we did, we rewrote the one above, and it does work. So I guess we can keep it, because that is the GGX trope rights one. Why is that disappearing? Yeah, it's difficult to see with the very bright sky, I guess. Yeah, it's just very small. That's cool. Right, so I think this is fine. So this is identical to what is above here. So we can simply delete that. So that is our GGX true, right. So now I want to investigate is, like, what about my geometry shadowing function? The Schlick-Beckmann one. We So the Schlick-Beckmann, how should that look? So roughness is going in here, so we should see it respond to roughness. But from memory, I don't remember, did it change? Because I remember at the start of the stream when I said it's because the roughness, it changes, it reduces how bright that is, but then we changed it and I think it did. Yeah, we can't observe it changing here. And moving the roughness slider. Bizarre. So rough. Okay, so roughness is definitely going in. So it's roughness divided by 2, so it's between 0 and 0.5. Then it's basically between 0.5 and 1, right? So this is between 0 and 1. So then when this gets multiplied between between 0 and 1, and this one's between 0.5. Wait, sorry. Yeah, 0.5 and 1. So this could half it at best, and then also keep it the same. And then after that's going to add 1. Sorry, add 0.5 at best. 0.5. So then you're getting basically between you're getting between 0 and 1 for this. And then you're adding 0.5, so you're probably getting between 0 to 1.5. So that should change the value. Like as you increase, but yeah, I'm not sure how it would be if you change the roughness, how that would change this value though. Does it just stay the same? It wouldn't stay the same. So is my debugging thing correct? Because I actually repeat the line here. Material roughness. So when we see it here, geometry, you increase the roughness. So no roughness is like that. Roughness is like this, and ours always looks like this. So should we look at the geometry function here? So that's the visibility term, I think. This one definitely looks different. It's because it's inlined. Probably. Yeah, here they square it. Let's look at the what is it called? The Smith geometry. Yeah, it's a G1 term. Where's the... It's not GGX. It's Smith Beckman, isn't it? Oh, Schlick Beckman. Schlick. Right, so they got a bunch of... Got a cheat sheet here. Hmm. It's probably a good read. I wonder where the right, this looks decent. Nice and quick, I reckon. So specular BRDF reference. I tried many different options for specular BRDF, specifically tried different terms, cook torrents, microfacet, specular BRDF. Yeah, so this is what it is. The cook torrents is the D, normal distribution, F, Fresnel, G, geometry. So these are the bits that I guess are configurable. There's already comparing different types of testing, being able to swap them. Right. So normal distribution function, we just looked at that one. But yeah, there's the GGX true bridge rate. So that's the one that we used. Interesting, we can compare it with this actually. There's the Beckman, Blinfong, and GGX and anisotropic. So yeah, this one I guess we can use later if we want to get that. Hey, you're not so red. Yeah, things doing good, man. We got the reflections rough now, so I basically downsampled the cube map. So we got all the MIP levels down to about 4x4. So you can see the sky there and the ground there. And as we increase the roughness, we get a rougher reflection now. So you can still see the ground in it, especially if you have metal. But yeah, also got the Fresnel working. So, a bit of rough there, Fresnel. Oh, it's the metal. Is it? Yeah, I guess you see more Fresnel and it's plasticky. But you got that Fresnel working good. So the reflect ray gets this. This is really, it just gets in the way now. I should disable this debug drawing. But the Fresnel, when it's dielectric, for the reflecting ray, yeah, you already see it now, which is great. So those are things we've improved since last time. We're just double checking everything, making sure everything is decent. But yeah, how's things going with you? Hope you're having a good weekend. Yes, this looks like a good link. The blog as well is, rants, basically, a ranting blog. Let's double check our Trowbridge thing. GGX. So you square. Yeah, alpha 2, that's squaring roughness. At the end of the day, you're dividing that, right? So there's the division at the end of the day. Then you want to take your n.m, m being, I guess, the norm. Let me define alpha that needs to be used for the following equation, alpha squared. So it's saying that you need to square alpha again. But it's saying it's squared here. That's weird. Also, what is m? Is m meant to be, I guess it's the normal. Wait, normal and half direction, I guess. It must be the half vector. But yeah, so there's the m.m squared. So n dot h, that is squared, multiplied by RT take 1. Yeah. And then you plus 1 after that. Then you square that result, which is here. Yep. Then you multiply it by pi, and then that's the thing you divide by. Nice. Cool. So that's correct based on that. That's good. I'm gonna get a little busy with the work. Other than that, everything's great. Awesome. That's good. Good to hear. You gonna enjoying that sun? It's summertime now. So what is next? Yeah, geometry shadowing. Term describes the shadowing from the microfacets. This means ideally it depends on roughness of the microfacet distribution. So basically, yeah, how much of the microfacets get in the way of the light that could come your way, if you will, I guess. So shadowing is blocking the light. Yeah, ones that block the light. So there's a Smith one. Smith is interesting. So it seems like it. So the following geometric shadowing models use Smith for their respective normal distribution function. Smith breaks G. Oh wait. Smith breaks G into two components, light and view, and uses the same equation for both. How to find G1. So what people say is that the Smith model is basically the one that just is more accurately represents what goes on in real life. How to find G1 below for each model and skip duplicating the above equation. Right, so G1 is below here. So there's Beckman. So what is this again? Schlick-Beckman. Yeah, this is the one that we're using here. But I guess the other one... Right, so let's look at Schlick-Beckman. Oh yeah, that's what I wanted to look at in the normal distribution. They were saying that alpha is roughness squared. So how does that make our normal... Let's call this A for a minute. Because they were squaring their A again. Which was just really weird. So let's look how our normal distribution function looks now. And then we'll get back to that shadowing thing. Because I want to see like how this affects. Does it make our... Because, okay, if something's squared, it means that... Wait, let's turn the intensity down on that light. So if you square 0.5 and 0.5, it give you 0.25. So it would go... You'll have a longer entry point, right? So maybe this does make better sense. Because I was saying, why does it disappear so quickly? Maybe... Yeah, I think this is better because it will fade... Yeah, specular highlight. It actually exists around for longer, so maybe it is better. Right, so we should define alpha as roughness. Alright, so swapping alpha for roughness was not a good idea. We should change this alpha So this blog is saying that alpha should be roughness squared. Right. Cook torrents. Right. That gets a bit of alpha in there. Let's rename that to alpha. Now, alpha, when it gets passed in, to the BRDF thingy. No, it's material in here. Alright, so alpha is equal to roughness squared. So we look at material. Right. So if that wants the square root of roughness, obviously squaring it's not going to help. So that'd be like 3 square roots. But when pass it into cook torrents, it goes in there like that. Cool. So that should be an improvement overall. Because I think a lot of those formulas were actually wanting that. So as the thing gets more rough, the slope of it, of how the value changes. Yeah, so that's cool. That's better. So if we look at that geometry, it's still got the same problem, right? Right, the geometry function is now changing. It's got more of a sharper... Did we observe this before? The alpha change? It was more of a... It was just always like this, but surely squaring it shouldn't have changed anything. Let's double check that quickly. Let's comment that out. Put the music back. Let's take a look at it now. Let's go to the geometry function. Let's bring the intensity down on that light. We should really just be viewing it without all the lighting applied on top. What am I doing? Changing the roughness. It is changing still. What did we change? Oh. I don't know. I could have swore it wasn't working before. We didn't change anything, did we? Alright. So let's just double check this against the equation at least. So we've got a bit of k. K is alpha square root of 2 divided by pi. So I guess ends up being 0.5. So it's just divided by 2. Let's throw that into a calculator. So square root. So 2 divided by 3.14. And then you square root that. That's one square root in this word. Right. Bit of Google. Square root 2 divided by... That's definitely not what we've got. So I guess we can comment this version out. Alpha multiplied by square root of 2 divided by pi. Then it's got your n dot v normal v vector Approximated Smith. Oh, there is another one. Schlick GGX. Which is divided by 2, right. Approximated the Smith equation for Beckmann. Warns that the Schlick approximated the wrong version of Smith. So be sure to compare the Smith version before using. Alright, so there's a Beckmann Linfong GGX. And then a Schlick GGX. So this is actually a Schlick GGX one. For Unreal Engine 4, I used the Schlick approximation and matched it to the GGX Smith formula by remapping K. Right. Interesting. Yeah, none. What? Oh, the Fresnel function. Okay. Yeah, we know that one's fine. Interesting. So I guess we can just go back to the Schlick, but its name's wrong. It's actually Schlick Beckmann GGX. Technically. Oh, was it Brian Karras' blog? Fair play. The guy who made Nanite. I can just imagine the blog in his voice now. There we go. Like, very enthusiastic. Right. Yeah, so I guess, you know, they're both kind of the same, computation-wise. That'll just be a constant. The question is on how it looks. You know, that was Unreal Engine 4. They've probably changed it since then. Maybe. But yeah, I don't know. Let's look at the shadowing. But yeah, it's somewhat very similar. So this is going to be less. That's just going to be more of it taken away. I don't know. Let's just keep that one, but let's just name it properly. So Schlick Beckmann GGX. That's what it actually is. I'm glad it's all in one place, so I don't have to look everywhere on the internet to find out this stuff. Right, so it's the Smith Schlick Beckmann GGX. There's too many people just for a small bit of maths. Right, optimize. Be sure to optimize the BRDF shader code as a whole. I choose these forms of equations to either match the or demo code or demonstrates property. They are not in the optimal form to compute in a pixel shader. For example, drop in Smith GDX into BRDF denominator. We can have this. Right. Yeah, you basically... Yeah. Because you're calling the same function. This... Wait, where's x? That's obviously... Oh, we didn't check the function out, did we? But yeah, I guess a lot of this could be quite similar. That's cool. Huh? Beckman. Yeah, obviously the compiler will sort a lot of that out, but it's good to hand optimize stuff anyway. Sometimes. Schlick Beckman. So anyway, yeah, so n dot v, so x in this case is our v. You're at the end dividing that by something. N dot v multiplied by 1 take k plus k. That's it. Cool. Obviously k just changed there. Right. Good. So I think they're all looking great. We should now check the metals and make sure the metals look good, I guess. But we should also just use the night mode. Let's look at the night mode. So here's our cube map. So it's the Yokohama day. There's the Yokohama night as well. So we'll load the night versions in. Let's go and see what those look like. Right, it's quite bright actually, not gonna lie. But now we're seeing... That looks pretty cool. So this is like the plasticky look. We're seeing the Fresnel on the edge there really show. That's pretty cool. So let's increase the roughness. Do you see that sort of... That's specular though. Yeah, I wonder we want to see... Yeah, I don't know. Okay. Then we increase the metalness. This is a metal ball. We see lots of like flickering when we move. So obviously, when we see this from far away, it probably just needs to select a good MIP level. Yeah, so we probably need to change the MIP level based on the size of your pixel to texel space as well. But yeah, what am I looking at? Roughness. Does we increase the roughness? That really shows there. So this is like apparently a metal ball. And then there's a very rough metal ball. You can really see it's kind of low res though. Like a low res building in there. Perhaps we should... I am taking the average. Maybe there's something else we can do. Yeah, I'm just taking the average between the pixels. Maybe that's fine. If it already comes out a bit blocky, maybe... There's too many MIPs. And that's just a bad idea. So we put mellowness all the way up. Roughness all the way up. Not rough enough. It doesn't go blurry enough. So we should probably... We had it at 10 before. Up the metalness, up the roughness. That's fully rough. It's a bit better. But I don't know. Yeah, you need to, what's great is this is okay. But as we get further away, you want the roughness to also change. I want it to get rougher. There's a mathematically correct way to do it. I think it's involving with a cosine kernel instead of your implied box kernel. Right, what do you mean by the cosine kernel thing? I don't quite understand that. Yeah, for blurring the environment. Yeah, because I'm doing it as a 2x2, aren't I? So, do you mean that I need to sample in a different shape or something? How long did it take me to make my first game engine? I don't know, it's quite a broad question. Yeah, I don't know, it's quite like, it depends on the size of the game engine and what its capabilities are supposed to do, really. Yeah, I know, but like, what was the first game engine, really? Well, I made like, uh, I don't know, takes months. Yeah, it was a long time ago. Take about a few months, maybe. And also, yeah, it's a bit of a meaningless answer because it's like months to do what? Like, what is a game engine? Like, just you don't know if I'm building like how complete it is or what features are in there. Do you think there's a way to do the blurring like a cosine kernel? Have you got any links, Cranston, for anything like that? Hey there, Render Goblin, how you doing? Yeah, different shape and different weights. The shape should be a circle instead of a box. The weighting should be cosine pi divided by 4 times by sample radius divided by circle radius. Interesting. Okay, this is from memory never implemented it. Right, interesting. Cool. Right. That's interesting. In the future, we're gonna do some form of like GI. When I do some form of like GI or something, I think I might use that yeah. It's gonna have to be a cube map still, I think. But there's gonna be probably some probes about and maybe they'll do some downsampling as well, I'm not sure. A paint map based GI. What is that? I'm good. Might have a shameless plug my games on sale for $2. Sure thing. Shameless plug. Shameless. Use a 3D texture live volume. Right. Paint map based GI. Yes, use your 3D texture volume, but then you get light leaking, right? Be careful of light leaks. Leaking lights. Where's your latest update? Vroom. Hmm. You got little like, vehicles, hovercrafts. Awesome. What am I doing? Yeah, so I guess when we get further away, we need to sort that problem out. Small update, nothing major. I've been reworking the render pipe. Cool. Yeah, I think we can ignore that problem for now, where stuff is far away. But I'll keep it in mind. Oh. Specular IBL, image-based lighting. We set up PBR in a combination of the image, pre-computing a radiance map, and the lighting's indirect diffuse portion. And this helps to focus on the specular reflectance. Right. I've not already done diffuse, have I? I guess I've done diffuse. No. I did Right, this is interesting. We should probably quickly jam over this. Sample spherical. Right, we're just using a cube map. Um, right. Um, Now you have a cube map. +1. Right, so that's like a linearize or whatever. Or something like this, or... Yeah, that's a gamma correct, sorry. sRGB conversion. Right, irradiance. Uh, so what's up with your PBR? How are you doing the metallics and GDX and specular? You can use a single image spherical map for development. Yeah, we're doing cube for now. The thing looks like IBL for reflection layer. No biggie there. Kind of have to do it that way unless you want to go balls rebound bouncing, which games don't need. Yeah. Yeah, you definitely need the cube map to exist. Or the environment map at least. Right, so irradiance. So interesting. So they're producing it in a radiance map. They're going over all of the... They're producing a sample vector, sampling from the environment map, producing a radiance. Um, As described at the start of the chapter, the main goal is to solve the integral for all diffused indirect lighting given to the scene's irradiance in the form of the cube map. Environment map. We know that we can get the radiance of the scene, light point, and probably the right. Okay. In a particular direction by sampling the HDR. Yeah, ours is not HDR, by the way. Ours is LDR. Environment map in the direction of that to solve the integral of sample scene's radiance from all possible directions within the hemisphere. Oh, this is computationally impossible. Yes, this is why we downsampled the cube map. So they're downsampling it here. Right. So we should probably produce... Oh, so that's what this was, is the irradiance map. Where is it? This thing down here is the irradiance map. Channel 1. Right. Spherical image is not too hard in a shader. Want the formula? You can use matte caps, light spheres. If you want a radiance on a separate map, use spherical harmonics. Yeah, I'm not really sure how those kind of work. I've tried to research into it, so I'm not really sure if I want to use them if I don't know how they work. But yeah, I know you can remap the UV into a sphere into like a flat UV. Is that what you're talking about? But yeah, cube maps just work out okay for now. Did I close the... Here we go. So maybe this isn't a downsample because you're just creating it the same res. Are you really? So the up vector normal. Right. Now what's left to do is set up the rendering code to convolute the earlier captured event. First we create the irradiance cube map again. We do this once before the render loop. So this one's 32, 32. Whereas the other one is 512, 512, I think. So you go over all 6 sides of the cube map. Yeah. Okay. Then with the irradiance, it's using the normal. So it seems like a downsampled version, but it's only... Yeah, it definitely looks better. I won't bother with the downsample. Spherical harmonics give you the convolution for a radiance that's equal to, in quality to a downsampled map. Okay. Give a visual example of how spherical harmonics work. A scene shown off the algorithm. A comparison of images from our approach used to obtain using standard texture mapping. A comparison of irradiance environment maps computed using the standard approach left and our technique right. But basically the same. Same for Grace Cathedral. So video from Freya has diffuse IPL and specular IPL chapters. Nice. Awesome. Should probably watch that. That's cool. How long is this? Because it's like, well, it's not C sharp. It'll be HLSL and. Right, it's about 30 minutes. Yeah, I think she made some shader visual shading thing. Yeah, that's cool. I'm not fussed about the format. I think it will provide enough detail, probably. Just want to sort of, yeah, I might watch this later. That's what I'm thinking about. Should I watch it later? Maybe I'll just skim through it. So she's got the fragment shader, diffuse IBL. Right, so that's already a cube map in some direction, right? I think she's already produced that map. That looks pretty decent, to be fair. And it's a specular's a different map. But yeah, here it is here. Yes, they've already produced the downsample version. Yeah, so what does she mean by diffuse as well? Because like, Right, I've gone back to the diffuse one. So diffuse lighting. Right. That just gets added together anyway. Diffuse light multiplies surface color. Right. Right. But then I guess if something is quite metal, you don't get any surface diffuse light. Um, the same headset. What do you mean? It's just headphones. What's the difference? um, I got another headset down on the floor somewhere. Okay, so then speculative on how's that different? It's the I'm not sure what it means by rectangle linear though, but yeah, you only use the reflect vector, right? So these she's the normal vector for diffuse, and then obviously the reflect vector, which we're already doing. Okay. And that's in combination with, so that'll get moved to, right, here we go. Now here's just in the MIP thing. Changing roughness, different MIP levels, right? This is what we're already doing. But yeah, it's not doing the similar, it doesn't feel like it's the same as what that LearnOpenGL thing was doing. That one was pre-convening the radiance map. Yeah, it's looking boxy, like ours is. I guess she's gonna fix that. So she's sampling it twice for diffuse and for, yeah, I don't know how. Oh, have a look at that. Yeah, use the Fresnel, that's what we're using. Right, it's just you didn't use the Fresnel for the. Hmm. Right. Advertisement. Right, that was cool. I think I understand what she's saying. That diffuse thing was right. There's diffuser radiance, but it feels like I don't know. I'm seeing specular here. Yeah, she doesn't do the filtering. Hey, Asher dude, how's it going? Yeah, I watched Planet of the Apes. It wasn't bad. It wasn't bad. Maybe she didn't actually do the filtering, but I think she at least talks about how it's generated. Been a while though. Probably yeah, better off light is definitely better, yeah. Also, Even to avoid the artifacts with the cube at face, you should probably want to sample the entire cube map. The vec3 of only the same face with a vec. Right. I see. Yeah, in that case then it might be good just to use spheres instead. Yeah, Render Goblin's saying you don't need using spherical harmonics, but I do not understand these things. We consider rendering the diffuse objects on innocent illumination as specified by environment map using analytic expression for irradiance in terms of spherical harmonic coefficients of the lighting. We show that one needs to compute and use only 9 coefficients, I guess 9 floats, corresponding to the lowest frequency modes of illumination in order to achieve average areas of only 1%. In other words, the irradiance is insensitive to high frequencies in the light, right, and is well approximated with only 9 parameters. In fact, we show that the irradiance can be procedurally represented simply as a quadratic polynomial, simply as a in the Cartesian components of the surface normal, and give explicit formulae. I don't know. These observations lead to a simple and efficient procedural rendering algorithm amendable to hardware implementation, and a pre-filtering method up to 3 orders of magnitude faster than the previous techniques, and new representations for lighting design and image-based rendering. Yeah, that's interesting. I've yet to understand more. I don't know what I want yet. I just want to try and see what looks. I would much prefer performance because it would be good to get it running on more hardware, right? We consider the diffuse objects. We consider objects with a range of diffuseness, right? Hey, Master Agent, how you doing? Welcome back. SVC debugger iterators for hash maps at least are the worst thing ever. Never encountered anything more slow. Probably goes over the whole array. Wait, it's buckets and stuff, isn't it? Are they even hash maps? They're like linked list things, right? My debug build runs literally 100 times slow. Oh, okay, debug. Oh my days. Wow. Bananas. That's why I didn't use standard library stuff. Well, there's been a reason why I didn't use standard library stuff. Lighting in most scenes is complex, coming up with a variety of sources, including area lights and large continuous lighting distributions like skylights. But current graphics hardware only supports point or directional light sources. One reason is the lacking simple procedural formulas for general lighting distributions. Instead of integration over the upper hemisphere must be done. Instead, an integration over the upper hemisphere must be done for each pixel. We represent such a formula for diffuse objects for irradiance. The key to our approach is the rapid computation of analytic approximation to the irradiance environment map. Right. For rendering, we demonstrate a simple procedural algorithm that runs at interactive frame rates and amendable to hardware implementation. No texture mapping is required for irradiance with our approach. With just 9 floats. Interesting. Yeah. 9 floats as well, and you get color. The main ingredient is a deviation of an analytic formula for the irradiance in terms of spherical harmonic coefficients for lighting. For rendering, the key observation is the Lambertian BRDF behaves sufficiently close to a low-pass filter that we need only the first 2 orders of spherical harmonics, e.g. 9 parameters. The simple form of 9 spherical harmonics makes implementation straightforward. A comparison of the images from our approach to the obtained using standard texture mapping. Which one is which? Left is standard, right is their one apparently, but I don't know if that... Anyway, I don't know which is which. Oh, it tells you here. Yeah, through this task, I need STL's... Oh, I need to choose STL, roll my own. What do you up? Time I need to feel... Okay, fair play. This feels wrong. The debug was average 10 times worse. 15 FPS. Crazy. Yeah, strange. But yeah, how's the job hunt going? Did you do well on how did the interview go? Oh, sorry, the test. Are you still doing that same test as you mentioned last time? The diffused lighting on all objects, so figure 1, in computed procedurally using our method. This is 1 frame from interactive session using the standard real-time programmable shading system. Okay, so this one at the top is purely their method, right? This one, figure 2, another scene comparing images obtained from our method using traditional way. No perceptible difference. The left sphere is rendered using the 128 squared environment map texture. The right is using... Okay, I did notice the right one did look different and a bit worse. I did see it. But what's the... Right, the top is a projection of lighting, the bottom mirror giving the incident illusion. Right. A different comparison where we put the actual radiance maps. Yeah, that one looks kind of similar. Right, so they got source code and stuff. They link to this. Radiance and irradiance, right. Just about that. Yeah, there's probably a shader toy for it. But yeah, so we've got a choice of basically doing this. We got 9, okay, it's not 9 floats, it's 9 times 3. Because there's a color in there, fair play. So... So So you update the coefficients and you're basically accumulating it in there. Right. Okay. So you take the whole image and you produce that. Right. Very mathsy. I don't really still understand what's going on. But I guess there's a shader toy for it. I think that's the way you spell it. SH visualizer. There you go, SH lighting. Think of a harmonic as a math description of gradients on a sphere. Calculating coefficients is crazy maths, but using the spherical harmonics is a simple lookup of 9 flows. Right. Oh yeah, 9 vec3s. So these constants be calculated from this website. Grace Cathedral. Calculate radiance. So then it's... So we just comment that out for a minute. Right. So wait, what? There's a flaw? Right. That's interesting though. Should wait to present in 2001. Yeah, I wonder if it's a good idea to use it. Take a direction gives you intensity. Yeah. In a special basis. Yeah, it sounds about right. I know that they use spherical harmonics to check in GI if there's a wall nearby, basically. If there's if yeah, is that right? If there's a wall, something like that, to avoid leaking, light leaking. Runs at 70 FPS with debug build 2000 on the release build. Wow. Yeah, it's a big difference. Yeah, so maybe we should use spherical harmonics. So this just is a way of basically having a downsampled image. And you can compute it using this, basically. So this would be the per pixel calculation. You update some coefficients, but it seems like, oh no. Oh, there's only 3 floats. Hmm? Oh, coefficients. Where are these coefficients at? They're global? So it just sums it all. Um, it's just summing it all at the moment. in there. So after the other page mentioned the little pre-filter function. The program's pre-filter C provided. Okay. We'll talk about the function for a minute. So I guess there's a second step. Pre-fill then to matrix. No, it just sums it. These in avatar to make rendering faster. Awesome. Yeah, mults and sums because of how spheres harmonics work. Fair enough. Actually, there's a better way to think of it as it takes a bunch of coefficients and gives you intensities in all directions or equivalently in all points on a sphere. Coefficients are multiplied by corresponding basis functions given here. Okay, I'm not sure if my brain understands that any better. So yeah, this is what we saw in the shader toy actually. This is probably robbed directly from the shader toy. When we searched for it, or at least we saw it here. There, right? Zoom. So sphere feature. Okay, 4 bands of spherical harmonics functions, or atomic orbitals if you want, for reference and fun. Ah. So there's that version, there's these versions. So a better way of thinking it is a bunch of coefficients that gives you intensities in all directions, or equivalently on all points of the sphere. The coefficients are multiplied by the corresponding basis functions given here. I'm not sure. Okay. Right. I think I get some idea of what you're saying. Like when you're building it, it's using these. Oh my days, where is that link? They turn it to a matrix here, that's a bit. But yeah. So I guess. Right, then after the matrix. It needs to be turned into a matrix after. So every pixel, it updates the coefficients. I wonder how you could do this highly parallel, basically. I think you can. Yeah, there's a global coefficients variable, basically, right? Yeah, lovely global. So maybe you just need an atomic, and you're just accumulating the color. Yes, it goes over every RGBNA for a pixel, and accumulates it specifically in, right? I can see that. And then after you get the coefficients, you condense it down into a matrix. Well, I don't know if it's condensing it. But anyway, if you put it into a matrix for some reason, then I guess in the shader, this is just feels so silly to do this though because I don't understand the maths behind it. But it doesn't look ridiculously complicated though, in terms of like the amount of code complexity. the understandable approach is just compute in a lower resolution version that does some kind of like circular sampling. Yeah, but he says there's a function rate. Oh, sorry, I'm looking at the wrong shader. Right, calculate radiance. Then this is the matrix. Is this even a matrix? Well, those are the coefficients. The little C program prefill provided computes the spherical harmonic coefficients from light probe images in the floating point format. I used the p-value tool from the radiance package on Ubuntu system. Oh, great. To convert the angular light probe image into HL format to float point format with the following command. I decided to modify prefill to output values with a factor applied to the coefficients. Then he ran the program, that floating point value, okay. Right, so if we take a look at the program that he's referencing, it does a 2 matrix at the end. So it's obviously outputting the matrix. So you need both, right? You need a pass, you need two shader passes, one that does this per pixel, and then one that does, yeah, that's not too hard. Well, it's not 2 shader passes? So just use some janky blur. But yeah, I don't know. I might need it in the future when I do GI, so maybe I should just put it in. Maybe. Or maybe I might just use a blurred cube map because, yeah, we'll see. I think about it. You pre-compute the coefficients and store them and use them like a cube map. So it's just a single pass then. Thank you, Alex. Appreciate it. Render Goblin Man, you're throwing me all over the place. You're throwing me all over the place. You're like, bro, listen to me, bro. Use spherical harmonics. They're way better. True. True. Yeah, I really don't understand them yet, but maybe in the future I will. Probably a good approach. I kind of get what's going on. But yeah, probably not a good idea right now. So back to this. There's like this version. So it generates some irradiance. So based on a direction, if you will. So it's rendering the irradiance map by just blasting. Let's see what it's doing. So it's building an irradiance map by basically rendering yeah, like a flat plane, I guess, against the direction of the was perpendicular to the cube map. And then it's probably just going over Hmm. But yeah, I think that's fine. For context, in this case, it was not clear. SH, at least no coefficients, are only good for approximation for perfectly diffuse objects, e.g. max roughness. Oh, is that true? Right, but not if you're going between them. Yeah, but maybe you take that result and then you lerp between the non-rough version and the rough version. Maybe. That's just a guess. Yeah, this is looking way better. But yeah, so we could probably improve the cube map. Because apparently there's a diffuse one, a specular one. I'm just using the specular one. Supposedly, according to that video we watched, there's a diffuser radiance, and there's going to be specular radiance. So I guess we could produce an irradiance map. We just ray trace through to the cube map, and then produce, or in the environment map, and then produce a radiance for that pixel. A radiance up vector normal. What does it mean by normal? It's that along the hemisphere probably. Sampling the hemisphere, right, and then produce the irradiance and store that in. So I'm sure they launched that lovely thing across all 6 sides. Change the view. Right, we could have a bit of fun doing this, I reckon. Should we produce an irradiance map? Yeah. Let's do this because I think we want to have a good base example, and then when we do some form of like GI, we will know, our PBR formula will be more correct, if you will, or the way it's implemented. Because right now, we've not really got a radiance map, we just use the environment map. Yeah, so let's produce that irradiance map. Then there's diffuse here. It says so we got this in ours. Irradiance times albedo. But then there's our albedo. Lambert. It should fit in here somewhere maybe? I don't know. Then ambient is KD times diffuse times AO. We don't have AO at the moment. Okay. So we need the irradiance map. So it should be quite simple to do that, I reckon. We'll render so if we produce another, so this downsample one will eventually go away. Wait a minute. So how this one works is it uses the high definition one, channel 2, then it has the irradiance map in channel 1. And it also has a spherical harmonic irradiance as well. Down these spherical harmonics. Right, so he's already got the coefficients written in there. Fair play. Fair play. How much does this affect it? Right, that's spec... No? Yeah, that's specular. But for diffuse, it already affects it. Whoa. Okay, so it's in the... Right, so the specular was kept as a cube map if you were on already a cube map, but texture. If you put the EV in there, it won't be correct. Yeah, okay. So the diffuse is using the environment map, right, got it. So I guess we need two different ones. There might be two different cube maps. One for diffuse, one for specular, maybe, I don't know. So irradiance map. So with the irradiance map, probably gonna be a similar sort of thing there. So the dimensions on this, they did 32. I don't know. Just give it a go. It shouldn't be too hard to write another shader for this. Where's the downsample cube map thing? So basically we just need to render the irradiance by just sampling the yeah, some really easy examples follow with these spherical harmonics in there, but the rest of it is quite simple. Downsample. Wait, what are we calling? Render irradiance. So we get the cube map in there. So this we use a sample cube map. That is the source. Bit of source. And the destination is a bit of cube map. Yeah, 2D array. One of those guys. Destination, sure, have a bit of that. Bit of layer in there as well. Right. So let's just get the basics in. Render irradiance map. So the basics is, if you go out of bounds, don't store anything. We want to produce a final color, and then we want to store it out into there. The rest is magic. I'm about to fill in. So it's basically this. You gotta know your normal, so the normal needs to come in as well. So irradiance the up vector, that's correct for me. Normalize a should be 3 cross cool sample delta and our samples, whatever that means. That's not even used anywhere. Concerning. Oh, it's used at the end. Whoopsie. So it's just number of samples. Then at the end we've got a bit of pi in there. Always need a bit of pi. Bit of irradiance. Right. Mol. Scalar. Pi. There's already a float. Samples count. Cool. So that irradiance, you're gonna pack that down and then turn that into a sRGB, I think. Maybe that's a good idea. Maybe not. What did they use the create the texture again? What format? There's a format somewhere. Run out loud. It's 32, wasn't it? There we go. RGB float. RGB, okay, so it's floating point. Probably not a good idea to pack. So, yeah. We should probably... 16. We should probably just make it a float 3. I don't like this example for line up in GL. Why is that? So okay. Sort these out quickly. Complicated. Well, isn't lighting complicated? They're doing it. It's a bit more of it's a better downsample, if you will. We've already got it. We're already doing the downsampled version. But it comes out very blocky. For environment map. So this is sampling for the direction. Because we're in a compute shader, we should obviously use sample level. Right, so this would be the color. Environment map. Did we get that in? What did I call it again? Let's call it source, innit? Alright. We should probably call this the environment map. Right. Climate linear sampler, direction, sample vector. Cool. LOD 0. So what we would like to do is basically produce, we're going to accumulate to the by mol s oh yeah. Thank you, Benny Montana, so much for the thank you for the sub, appreciate it. Oh, thank you, Kadema. Thank you so much for the raid, appreciate it. How did the stream go? Welcome, raiders. We're currently working on PBR. We're improving our image-based lighting by following a bit of a tutorial. But here's our PBR at the moment. Got a bunch of spheres. We've got a little bit of UI to debug what's going on, so we can increase the metalness and the roughness. When these currently we're solving the problem where these things get a bit blocky when they're blurred. So we're trying to produce what's known as an irradiance map. So, but yeah, it's coming along. That's good. Java enemies are joined. No, that's cool. So it's C, yes, UCC. How did the stream go? Thank you for the raid, so appreciate it. Yeah, it's looking way better than it was. It just used to be a bunch of red. And now we've got like more like that proper shading basically. I don't know how realistic I want to go, but I at least want to have a PBR implementation and have a bit of play with that. Zoom. How's the memory management? Allocate and no free. That's what I'm doing at the moment. I've got a couple temporary allocators that I just reset once per frame, but most things are just statically allocated and we don't dynamically allocate at runtime. I don't know how the metalness is looking. I think it could look better. I definitely have to compare it. It just goes like that. I don't know. Increase the roughness. I don't know. Those spheres, do you generate them or are they meshes? No, these are ray traced spheres. So I just ray trace. They currently binned into screen tiles, but we're going to be putting them into a BVH after we've done the PBR research. There's a lot of shimmering going on there, and I think we'll fix that. Maybe fix that with this. So we're kind of trying to produce a downsampled irradiance map. So that takes the cube map, which is the scene you're seeing, and produces a smaller version which just has the light of, well, it's basically a downsampled version of the scene, but rather than box sampled, it's more circular sampled. That's what I'm getting at from this. So we've got like got a cube map, if you will. We're essentially got a little point and we're rendering like that. We're shooting an array. Got the near plane. Shoot an array at the scene. Wait. For every pixel we want to render, we're shooting a bunch of rays that are kind of close to each other, but end up at different points. And then I guess we're downsampling that based on a circle rather than a box. And so we're rendering into a smaller resolution cube map, basically. That's what this code is apparently doing. Yeah. People who knew maths wrote this code. I'm just copying it. But I get the idea. So I think I've got a... Right, seems legit. I do have to... Let's get this compiling. Oh, normal. Yeah, that's passed in BC normal. See, I wonder... I don't think I would need this if I remapped it to a sphere rather than a cube map. But this is cool. At least we can move to that later on. I'm not fussed about that. Tangent sample. Right, this is vector 3 stuff going on. So moles right, and then a bunch of adds. So it's kind of like, yeah, what you do for a matrix in a way, I think. Another add in there somewhere. No adders. Nearly there. Right, so there's a sample vector. What? N. Oh, wait. N? Where's the shader code? N is just normal, right? Can't see an N in here. Yeah, because any other one you got is normal, but I guess they typoed that a bit. Right, so you're adding, right, color. Ooh. Multiply color.xy or RGB. Irradiance. I don't know, we kind of need it as a... You know what, we'll make it a vector 4. Be a waste of multiply though. No, we'll keep it as vector 3. Because we don't need to pack it down. We've got to make sure we keep it as a... kind of like a HDR texture in a way. Implicitly cast to float. that. Cool. So actually, in our storage texture, we should probably store it as a float 3. I don't know if we have that type though. So I could manually pack it into. Let's just do a float 4 for now. I don't know if we have float 3 types. So we're just going to take the irradiance. Yeah, we do have it. It's just not very cross-platform, I think. Vulkan has float 3 types. Yeah, I think they were using like an RG. We can look at the texture format in a minute. Yeah, so we want to store 2D array times 3. Oh. Yeah, I didn't add it in here. Fair play. Yeah, I feel like we should probably have a custom packer which will pack it into a U32 and just manually turn it into some kind of fixed point or floating point per channel, and do like an 11 11 10 or something. But yeah, until then, we'll just do the heavyweight version. Yeah, so irradiance. Problem with the radiance is that it should be of 4. Let's just correct that. Rightio. That should be the shader compiling, no? I need to remove these doubles because if not, my compiler doesn't like it. But like doubles aren't supported. Alright, looking good. So with this now, we need to, so irradiance map, let's create that. We need a new texture format. So storage format, it needs to be 32, 32. It's horrible. Well, I could do 16s. Use less memory. Yeah, we can add this. Let's go around quickly, put that in. Bytes per pixel. 8 bytes in it. Channels 4. Name. Short name. Yeah, can it be used for a sample? Yes. Storage, yes. Cool, so now we just have to put that in the Vulkan side of things. Here's the lookup table to translate to a Vulkan format. VK format R16, G16, B16, A16. Apparently they don't have it. I think they do. Right. Whoops, I put spaces in it. float. Nice. Cool. So going back to where we were, that should all irradiance. Irradiance map dim. Okay, so now we just need to launch this shader for every side of the texture cube map. So here we did the downsampled version. Let's do it again, but this time for the irradiance, render irradiance map. We want a destination. So we're not doing MIPS anymore. Let's bring that in a bit. Destination layer is just layer. There is a Q environment map. That is this environment map ID. Destination is simply the irradiance. Then the dimensions that we're launching. So plop that in there. Right, that seems sensible. We are still missing the normal. So based on, stop check that. When we uploaded the cube map, it's this, so it's left, right, left. So this is the order. Right, left, top, bottom, far, near. So it's just much easier if we encode that in as some form of lookup table. Because if not, it'll just be a bunch of maths you have to work out, and it's just far easier to read. One minus one. I think that's right. We'll be able to know quite easily if it's wrong when we see in the texture viewer that we've got. So normal equals normals layer index. So we're launching, synchronizing on two things. We're reading from the environment map, and we're writing to the irradiance map. And this is the shader known as render. Well, I think I closed the shader one. Excuse me. Render irradiance. Okay, so hopefully we'll launch this and it just works. So hopefully, right, so the stream dies. It means that we've indexed out of bounds and all hope is lost. And I'll be back right away, but it shouldn't crash. Excellent. So now we're going to open up the texture viewer. Boom. Irradiance map. Here it is. It seems to be giving us the same color. I don't think we're doing it very smart. Something clearly wrong. Or the way we're sampling or something. We're definitely setting every pixel though. I know that for sure. Yeah, that's what I was already doing, Render Goblin. I was already doing the linear downsample, but I'm trying to do it rather than a box. Like, we already have it working, right? No, not spherical harmonic. So the problem is with this version that we already have that's working, is we increase the roughness. It looks kind of blocky. Can you see it? You can see the buildings in there kind of blocky. I want to try and improve that. So we're doing this other version. And then after that, we'll try and make sure we get the diffuse irradiance and specular irradiance and see how that code plugs into the PBR shading code. Yeah, right now we're just trying to compute the irradiance. So I think we did it all right. Blur filter after downsample? Huh? Maybe. Oh, did I not change the format? Thank you. Appreciate the sharp eyes. Correct. I put the format in, but I never changed it like a Wally. What a champ. Thank you there, Looks Mum. Look on the hands. Right. Look on no hands. Let's see how it goes. No. Oh, yeah, it's up here, wasn't it? Anyway. So maybe we should increase the resolution a bit. Just for debugging purposes. So let's put it at like 512. Okay, so what we can do is we can color in per pixel what the so the first one is going to be right, the first slice or layer. So we can color in something something that we want to debug in here, and that might be helpful. Oh, yeah, so we can encode the normal maybe, or yeah, so we can encode the up vector. So what does that equal in the end? We could also just debug launch these. Right, yeah, I could use the debug drawing stuff, but then only see on the first frame. I have to run every frame if I want to see that. But yeah, I think what I can do, say up.x, up.y, up.z, 1. So we should be able to see a color now, see what that up vector is. It's green. Yeah, that's correct. And the right vector should be red. Right, it's black. So let's take a look at a bit of the maths behind it. So we're getting is crossing with the normal, and the normal is right. That should produce Z, right? So you're doing a cross of up with 1 on the... I don't know what's going on here. 1... So that should produce you 1 down the Z, right? Let's cross... Let's just put the normal in there. Double check it for a second. Where's the float for? Yeah, I'm using a float 16. Oh shoot. Yeah, that's true actually. No, I use a float 60 format. Yeah, that's true. It won't do the automatic conversion unless... Yeah. That is true. Yeah, that's probably the issue. We should do the... I don't know why. Right, let me take a look at that actually. That's a good point. Let's bring in the 32 version as well. Alright, let's change all that over. Doesn't matter, it's unoptimized at the moment. You can optimize it later. So bytes per pixel is double that 16. So we could say the storage format is this. We have to pick an underline format. Yeah, no. Let's do that one. Right. Let's try that out. Alright, so we're still getting just a fade. Or just a sort of like single color. Same per pixel, which means it feels like it's going the same sort of way. Let's try this again. Right.x, right.y, right.z, 1. Now, we've got a couple of debug modes in the texture viewer where we can say, hey, make it white if it's a non-zero value. So that's an extra, so it's black. We can say, hey, make it white. Obviously, it's not white. So there's clearly no non-zero float value. If we use an int, it's saying it's blue. Probably because the value, there's like 1 in the alpha channel or something like that. Right, so that's a bit bizarre. What's up with my cross products, basically? Because we saw that normal up was green. That's Y. Normal was red, so X. So that should produce Z, right? So it should be producing the Z-axis, but it's not. And I'm pretty sure I've used cross product before, right? Let's quickly just double check this shader gen. Sorry. Spivvy dis, and I want to find cross. Yes, this is the extension cross. It does use it. Let's look for cross. Have we used it? I've not used it anywhere else. These are the only 2 places. Let's look at the code gen. Up, normal, composite construct. Right, this is post optimization, I think. Huh? Alright, there's a few places. A couple of crosses in there. What's that cross? So there's a single cross in the irradiance. So it's optimized out. Irradiance map. We need to do the cross. Hmm. Three, 4. I guess that's a constant somewhere. There's a 1, 3, 3. That's loading the normal or something. Yeah, it's found a way to optimize it down to 1 cross. And then a normalize. And the other one is built. Yeah, I don't know what's going on. It's something feels dodgy. So what we could do is try and reproduce it here. Let's do it without the normalize for a moment. Let's see if that... No. So I don't mean that up. I meant hard-coded up. This is if you hard code it. Sorry, this is in CPU side code. This is swapped out for the SPIV intrinsic in the compiler. We could try manually doing it here. So B would be normal. Only Y would be equal to 1. Oh. No, maybe we can look at the maths in a sec. It's still black. So so our normal is 1 on the X. We're going to 1. So yeah, it's going to be on the Z, right? 1 times. Yeah, 1 times 1 take, 0 take 1 basically, so it'd be minus 1. Let's double check that one more time. BC normal. So I don't know why in the texture viewer it's not showing up. Is it the texture view that's the problem? You can run this for each pixel. Yeah. Yeah, so basically the normal points to the, from my understanding, at least when I followed it, you got like a hemisphere, and the hemisphere is pointing in the direction of the cube map layer, or the side that you're, yeah, so we do get blue, so it's working, but this one isn't. It's negative. So it's, it is working, it's working. Negative values. That's why it's black. So, right, what can we do in this texture viewer? To view -1. Better. Negative values, how do we view those as colors? Yeah, something to think about. Yeah, it's a negative value. So we see black, it could just be a negative value. That's something to keep note of. So it's correct. So, right, why is it radiance then? At ABS and modes. Yeah, that's probably a good idea. So you could change. Yeah. Because sometimes you want to know if it is negative though. So I guess. So I think there's a different way you could view the negative data, but you can't, is there? So when it's color. Yeah. Right, this is a color viewing anyway. But yeah, we should probably have a way of viewing a float. And that should support, and int as well should just support signiness maybe. Right. Yeah, it's interesting. Yeah, I'll think about it for maybe a floating point view mode. Yeah. Um, right, so what are we doing wrong here then? See, we know our vectors are fine. We're going over and sampling based on some. So we definitely got the environment map in there, I think. Then there's the cube map, sample vector, get back a color. Then you multiply the color by sine and cosine angle. And you're accumulating. Right, that's interesting. Let's just double check it with this code here. Sample delta. So there's a delta. That could be very small. Let's up the delta of that. That's probably way too much. Because this is in normal space, right? Ain't good. But yeah, so you're going over. Right. Okay. We're equal to Cartesian in tangent space, right? So, let's double check I got this all right. So sine, cosine. Right. Okay, so maybe the sininess. Sorry, the not sininess. The coordinate space is probably wrong. Like, we've probably got to flip it around a bit. I might have misunderstood earlier, but understanding is you want normal to point in the currently calculated pixel, not the center position of the face. Ah. Yeah, that makes a ton of sense actually. Yeah. And I did say that when I explained it when people were coming in for being raided, but I think when I wrote the code up, I didn't do that, did I? No. So what we actually need to produce. Right, I see. We got a function for that. Yeah, it makes a ton of sense. So we've already got one of those functions. Ray direction. Field of view. You probably just need it without the field of view though. Yeah, it's probably as simple as doing a. So that puts the screen dims in with a bit of a coordinate. Right, so we want it without, like an orthographic version, basically. Rather than a perspective. So if you have like an XY, so get the half dimensions. Half dimensions of the screen. Compute. So you make it relative from the center now. I guess it's just without the divide by, put town field of view, maybe. Oops. That's cool, Render Goblin, no problem. So, wait, or do we want a perspective? No, you probably want a perspective actually. You want to visualize the pixel in the box that the cube represents. Then alter direction from the origin to that pixel. Right. I see. And to the center of the pixel as well. Yeah, that's cool. Huh. Have we got the code for that already somewhere? Right. So they're passing local pos from the vertex shader. And then they're sort of interpolating it. Fair play. It's probably quite easy to work out. So, got the pixel. To origin 0. I guess in cube space or whatever. Right. I got an idea. So we definitely need the dimensions of the screen in here. Yes, you probably don't need a different direction for every. So the x will be destination coordinate dot x plus 0.5 then I think it's all about where you set the z, and then you have to normalize it. So the z will have to be set forward somewhere. So it's probably half the dimensions of the screen along with the, well, it's kind of square, isn't it? So it's half dimensions of the, oh, not the screen, of the actual, so radiance map dim divided by 2, and then you normalize that. I think that makes a bit of sense. I think that makes sense. So let's replace it for that instead. So I don't think you need that thing passed anymore. Right, we're seeing a shade now. It's all the same shade though. I guess we would need a normal. Oh, yeah, sorry. Good catch. I was thinking that and then good catch. Right. So it has to be centered. Huh. Yeah, there's also something else. So just Yeah, so that's just still producing the same solid. Yeah, so it's not changing for every layer now. So I guess we do have to have the that sort of facing direction still has to apply. In some way. So I'll divide by 2, whoops. Right. But yeah, so we still got to do the facing direction now. How can we do that? So we have this, by default, it's just going to go up, basically, isn't it? X, Y. Yeah, we're going forward. Whoops. It'll just be going forward. So it does like as if we're looking forward at it. But yeah, I guess we want to get one face working. Let's try and get one face working first. They're all going to look the same. That's cool. Right up times normal. So imagining it where you've got like where your ray's firing, you got the up and the right vector, which are perpendicular to that. So this is basically rotating around. It's probably rotating a ray around this part across this plane, if you will. Across this plane, it's rotating rays around there. And compute a bunch of samples. Oh, the hemisphere. Right. The hemisphere. Of course. So, and I did increase the dimensions just so we could see more. Yeah, I made it 512. Theirs was 32. I made it 512 pixels just so we could see. But it's right, seems legit. This could be wrong in terms of my coordinate space. I've had to change. Right, so where's that two spherical coordinates thing? We've already written this code before. Yeah, so is it this one? Right, let's put it in here and figure it out. So x cosine phi. Yeah, I think these are a little bit off for my coordinate space, maybe. It's fine. Tangent sample is a transform from phi theta. Right. Spherical coordinates to Cartesian coordinates. Yep. They probably switched phi and theta. If you start renaming them, don't forget to also do that in the loop. Okay. Right. Let's just see how this looks. Right, we're seeing something slightly different. You're saying rename them in the... Yes, we reordered them a bit. Yeah, I don't know. So 2 times pi do the whole, this would do a hemisphere, isn't it? Right, see what you're saying is you should probably swap those around. Like that. Oh shoot. That might... But then it just... Isn't that just doing the same thing? Right now it's black. Great. What else could be wrong? Maybe that's still a part of it. Let's make sure I got this right. So it's adding, it's summing. Plus n, whatever that n is. Maybe the n is wrong, but n should be normal, maybe? From both views, we take the spherical coordinates, convert them to 3D. Sample vector, convert tangent around the normal. Yeah. Yeah, that seems correct. Yeah. Right, let's just double check. So cube map. We should probably just set alpha to 1. I doubt that that's the issue, but should double check it just in case. Right, still the same. So right, okay, that's correct. Multiply by right. Yeah. Multiply up. We're adding the normal z. Yep. Multiply, add. Cool. Seems correct. Up linear sample 0. Get the color back. Yep, then add. Accumulate. Then at the end it's pi. Pi times irradiance times 1 divided by samples count. Let's try and do none of this. Just see what we get. Right, very white texture. I can't bring the scales around. Linear color. Right, very, right, more than 1 to 28. So if we divide it by the number of samples at least. Wait, that's multiply. Yeah, 1 divided by number of samples. It's Tennis. Thank you so much for it, so I appreciate it. How's it going? How did the stream go? Thank you for the raid, sir. I wonder if there's a shaded toy for this somewhere. Have a play. Yeah, we're currently working on PBR. We're doing image-based lighting, just making it better. We have got a basic PBR setup at the moment. So we've got a configurable area we can play around. Increase roughness, metalness, and you see it gets a bit rougher. We're currently trying to make it look a little less blocky in here with the filtering. So yeah, we're just following a tutorial and seeing how we can fix that. But yeah, any questions about the project, feel free to ask away and I'll happily answer away. Is it image-based lighting? It's more like irradiance. Maybe a radiance map. It's not mapping. This is probably it. Spherical harmonic. Nope. Use Monte Carlo sampling method to get the irradiance map. UV. Put the UV in there. Compute the normal. Use direction to access the irradiance map. Thank you, Morris. Thank you, appreciate it. Thank you, Zal. Thank you, guys. How did the stream go there? Hits tennis. Thank you for the raid, sir. Oh, Inspector Time. Inspector Time, so thank you so much. Linear. Oh shoot. We're definitely doing it in linear, right? That's a bit problematic. sRGB. Oh no, we gotta manually do it. Yeah, that's a bit problematic, right? My reflect color is in. Shoot, I didn't unpack it. Whoopsie. Wait a minute. Isn't that problematic on a sample? Because it will do the filtering, like a linear sample in sRGB space. Isn't that problematic? Yeah, this all runs on the GPU. I've got a custom C compiler that compiles C code to SPIR-V, so we can run a subset of C on the GPU. So it supports running it in for the Vulkan API, basically. Yeah, I think this is a bit problematic, not gonna lie. Like, does it sample in sRGB? The linear sample in sRGB space? I think it is. Let's take a look at that, how that looks when we make it linear. So the spheres. So yeah, the background looks very washed out right now. We should change that as well. Let's keep an eye on that one. I think if we go to do we look at this? Yeah, it's not looking as bright as it was. So I'm wondering why the night one was so bright. Yes, that was so washed out as well. Man. So yeah, if we increase the metalness, now these things look, they don't look as washed out at least, right? Interesting. Increase the roughness. They're not as blocky anymore. But yeah, I wonder if the sRGB, I wonder if that sort of, man, I need to get rid of these. Hovering. BRDF, where's that? These. Just getting rid of some debug drawing. See, I think part of, so I wonder if this is problematic, and I think it is. Go up here. So you can see this sort of like line here. And let's see how it's sort of like blurry here. I reckon if we did this in linear space, this would look different. Just a guess. Like, I think it does the sample, converts it to sRGB, then does the bilinear. But I don't tell it it's an sRGB, so it doesn't do that. So now instead it does the sample, bilinear, then I do the sRGB conversion. So it's doing it in sRGB space, I reckon. I wonder where the sRGB comes in the pipeline. Texture sample, sRGB, before linear, interp. I don't know, where is it? Right, so, okay, I did implementations should perform the color conversion on each sample prior to filtering, but implementations are allowed to perform the conversion after filtering, though the post filtering approach is inferior to converting it. Inferior to converting from sRGB prior to filtering. So apparently it's not. Yeah, because I guess it's more costly if you do it prior, right? But maybe it's not so bad. Most images are sRGB. Don't have special processing when loading there into OpenGL while the shader you get the wrong image reply. Sure if that answers the question. But yeah, maybe it's fine. But no, you're wrong. But anyway, back to this thing. Yeah, we didn't do the we should be doing linear GPU linear. And then just make sure when we use the irradiance map, we don't do the conversion because it'll be in linear color space. Yeah, I'm looking at texture. This will still be wrong. Yeah, now it's really faint. Let's bring the white down. The stack of flows is talking about texture versus RGB internal format with how it does the conversion. You seem not to the hardware about the encoding. Yeah. Right. Yeah, I wonder why I didn't do it. There was a reason why. I visited it when I was doing the texture viewer. I need to probably. Why did I do it? There was a reason why. I think it's okay for the sample. Yeah, maybe we need to get it to do it. We could have a bit of a play about and see how it changes. Like, right, the reason is because the swap chain image couldn't be set to sRGB or something like this. Swap chain image can be sRGB format because I don't render to it like I use a storage texture and I store it in there, so it has to be unorm. So if you have it with a storage bit, the format can't be sRGB. There was something like that. Ooh. There must be a way around it, because I'm sure other games have this problem. And they don't do it manually. There's something that he's playing about with. Maybe it's just on the swap chain image that it's got the problem, so it shouldn't affect everything else, I think. Yeah, maybe we should add it in and just see what happens. Yeah, strange. So it has to be a render target. But then, like, yeah, we don't use... just a bit confusing. We'll see what happens when we try and make it sRGB by default. Let's just get it in there. Right, so that's in there now. Let's try and just set EV map to sRGB. See what happens. Right, so we boot up now. EV map is in sRGB. Let's see if it just still runs. It's going to double. Yeah, okay, here we go. Here's the validation error. Yeah, so according to the hardware that I've got, I guess other hardware supports it differently. But sRGB only supports sampled color attachment, so render target basically, or blitting, or transferring, but it doesn't support storage. So if it's got a usage feature of storage, you can't have sRGB. So you have to end up doing a copy or something to a separate texture. It's really weird. Yes, that's the reason why we don't have it. Just delete all that. Bloody annoying. Yeah. But yeah, at least we made that look a little bit better now that we caught the fact that we weren't doing the sRGB conversion. It's because render buffers are on the side of the GPU pipe and the storage on the other. Huh? I'm not sure what you mean. Yeah, it looks better with sRGB conversion at least. We still got to make this work. It might be best to run this every frame and just debug render a bunch of normals. Be a bit of fun. I reckon it's possible, right? Where is it? Render radiance map. So I reckon what we can do, right? Why don't we take this and just run it here? Or run it every frame? Or once. For one side. And all we do is we just say, given a world space position, let's draw a bunch of these normals and we just get to see what it looks like. So we can just say this sample vec, draw 3D, vector, world space, we'll put it in the center of the world. And then what I want to say is, here's the sample vec. It's going to have like some form of color, some thickness, 0.1 probably. Maybe it's a bit too big, I don't know. 0.01 maybe. Bit of color. Let's say like a red, I guess. And then do you want to Z test it? No. So I'll put out a bunch of normals. We'll see how that looks. So around 0, we should be seeing. It might be quite small though. I thought 0 was back here somewhere. Make him a bit thicker. Multiply them by 5 at least, so it should be a bit bigger. It goes through the rasterizer and ends up in special locations on the GPU. Yeah, I guess it really depends on the hardware, how they do it. Where's my red? They're running every frame, right? World space. One's a bit big, maybe? Oops. Be alright. Are they being drawn on top of or something? They should be just behind these guys. 3D draws after the damn UI for some reason. Don't know why that is. Yeah, should be. Let's draw a dead basic one. We should see where they are. So that should just be in the world somewhere. Nope. Let's put the profiler on. To tell us what's running. Should see the shader. Right, there's only one. It's not being done every frame. To like 400 milliseconds. What? That's like a long time. I didn't realize it was that expensive. Viewing that previous frame as a texture is so cool. Oh, right, yeah, you can view. Yeah. And you can go back in time as well and view a specific point it was written to. That's very handy. You can view all the textures live and take screenshots and save them and reload the screenshots back up. So if I want to reload a screenshot back in, I just rename one of my past screenshots. This is what we came from, guys, is this shading to PBR. So it's way better. Yeah, I can just change it to texture 0, texture 1. These names here, and then boom. There'll be the screenshots. Yeah, that's very... I should have noticed that was in linear space. Right, it's fair play. Oh yeah, I'm doing it across damn 512 resolution, aren't I? That could be overflowing. That could be part of the reason why it's so damn slow. That's a good point. Yeah, this should be running every frame. Oh, I'm inside the thing. Right. That in there. It wasn't running every frame. Right, they're there. It's running like 2 FPS. Right. So I've changed the step size, you reckon? So I only ran that once and it was really hindering performance. The slow pi is the for loops, step size of which is hard coded, right? But anyway, they're showing up now. So I'm curious about the amount of these. We're probably putting a ton of vectors in as well, which really doesn't help. But the step size, so you make it a bigger step. Let's just try that for a minute. Look at all those vectors. Boom. You can see them. I don't know how choppy they made the stream. But yeah, so they are there, which is nice. Make that 0.1 again. And then we should probably make this, I gotta remember though, what was supposed to make it 2.5. So choppy. So there's the vectors, right? They're down the z-axis as we thought. It's way too choppy still. I don't know what it is. Is it the ray traced? No, it's definitely this. Times 3, right? Do you only get one of those? Eh. I don't know. Those radiance systems when you change to 32, it's not like it's doing it. Shouldn't be this slow, right? Maybe it's all the vectors I'm drawing as well. But there's all the vectors, right? Vectors look pretty cool. Wait, each pixel probably gets... Right, let's put the samples back. Should be relative to 2 times pi equals 6. Yeah, I was seeing this. Yeah, I was keeping a note on that. Yeah, it definitely went over that. Yeah, it's doing one of those per pixel. It's good. It'll be good to see the normal though. Yeah, we normalize the normal. That's cool. Maybe this didn't help with the performance also. Yeah, ray tracing all those was just too much. But here's the normals. We can probably take a look at the samples just for one. I don't know why. We could focus on a single pixel, I guess, and draw a box. Draw a sphere. I do want it to be done a bit quicker. Maybe we can just not do anything. Just debug draw for me, please. Right. Okay, they're very big. Probably why some of the debugging stuff just looked a bit bad. Right. So there's one normal. Let's see when we unleash the beast. So all the time now. Alright, a bit too many, but it's... Yeah, it's a radiant still. I'm just making sure, checking my inputs. Right, so they all come from the same place, and the normals are all shooting out. Fine. So that normal looks fine. So the next one to check would be the radiant. Given this, right, draw that ball, but then draw all of these boys and girls in a different color. Draw them in like yellow or so, I don't know, like a green. And then you probably want to make it so that they're actually even thinner, because actually yeah. And to make it nice and quick, we won't use the radius result, so the compiler should optimize that out. Right, still way too slow. Increase the step. I don't know, man. I wonder how many steps we're doing here. It might be a lot. Let's make it 10 times quicker at least. Let's just see what we get. Right, there we go. Right, so it is across the hemisphere. That's pretty cool. It's not... Yeah. That's the corner. So... Yeah, that's looking pretty cool. So given that normal, so I guess if I increase, I don't know. I think we get a bit of time. You can watch it move maybe, but yeah. The power of debug drawing. It's actually quite unoptimized as well. It just ray traces against every debug shape for every pixel. So it's quite easy to put in. But at least we know that normal and that looks alright. You know? I guess the problem is probably in the accumulation code somewhere. Like I can change this so we could basically just take the mouse coordinate, right, and say something like if mod mouse like gfx global mouse position .x mod irradiance. What about the output that makes us unhappy? It's just one single color still, I think. Well, it wasn't really single color. Yeah. We'll look at that again. Crying out loud. It was kind of just like brown. But maybe that's okay. Maybe it's fine. We could switch to the daytime one and take a look at the compare it rate. Yeah, sweet. So if I move my mouse position, it's gonna, oh, for crying out loud, Y and Y. So when I move my mouse position around the screen, depending on the pixel, it will change which way it's looking at. So I can get down here. Yeah, so as you can tell, it's able to rotate and do all these things. Cool. So it's firing the rays out fine. We can tell from that. The color that was getting is like this brown, but I guess it's kind of like a dark map. And maybe that's... Maybe I need more samples or something. That was a 0.2, wasn't it? Let's not run this every frame anymore. Right, catch the Randy Goblin. Have a good one. Good to see you. Oh. Oh, what did I change something? So one, we've only got one direction. That's the first problem. I'm not fussed about that. What did I change? I did the sRGB to linear and then it missed. Okay, yeah. Let's change it to night to day. I want to see that one. Yeah, this looks way better now. Color-wise. But yeah, regarding what I was trying to fix. Right, so we're getting a bit of banding. No, it's not banding. That's just the resolution. Yeah. I guess we're getting a radiance. It's kind of upside down. There's the ground. There's the sky. The directions are all the same. That's something to fix. Not much masteration. We've just been trying to fix out the Get the irradiance map to work. You did miss some awesome debugging though. There's a bunch of vectors and stuff. But yeah, the irradiance map is still... I don't know what to make of that. I need to get the different angles to work. But I guess I can say that till next time. It's getting quite late here. You can narrow the debugging to get it phi and theta range to get less. Right, yeah, because that one of them's the hemisphere. That's the full circumference, isn't it? Yeah, whereas that would only be half. Wait. Oval pi would just be half. I don't know. Render goblin, you just need radio, but you just okay. Yeah, but I want to give this a go. This seems like an interesting way of doing it. Maybe I could do a radio blur. Doesn't matter how many samples you take, it's gonna be blocky if you don't blur it after samples. Yes, I'm bilinear sampling it already. Yes, I'm already doing the bilinear sample basically. See here. It just looked worse on that night one. Zoom. Yeah, you can see it. Just, I guess. I guess we already saw it on the light one, on the night one rather. Yeah, it just looks real bad. Maybe that's just the low res. Yeah, I reckon we can get rid of this. Maybe it'll look better. I'm just taking an average right now. I guess this would be an average as well, but yeah, mixed with a bit of a blur. Mm-hmm. No, I'm doing the bilinear interpolation on that. I'm just missing the blur part, basically. But yeah, right. So next time we're going to carry on getting this to work. We're quite close. We've just got to get the directions and probably, yeah, get the directions and maybe just for debuggability, just tweak these a bit and see what it looks like. This is like a low res bilinear interpolation. Yeah. Yeah. So hopefully this will end up actually better. But we'll see. Anyway, let's find someone to raid quick. I've got to go and collapse in bed. But yeah, the next stream Tuesday and Thursday. Shall carry on. ICC, but it's Portuguese. Right, let's roll. All right, check out the timetable for the streams, and there's a Discord I'm going to come out and hang outside the stream. All right, thank you, Chris. Yeah, thank you for helping me out. Good help. Right, have a good start to your work week, everyone. I'll see you all in a future one. Catch you later.